We are up to problem 18 now, and let me read the instructions here because it's rather lengthy. 18 and 19, I'm not going to do number 20 because it gets pretty messy, but 18 and 19, here's the idea. The instructions say, for the following functions, determine the following if possible: domain, intercepts, asymptotes, intervals of increase and decrease, maximum minimum points, intervals of concave up, concave down, and inflection points. And then it says, with all this info, sketch the graph of the function. So they're basically saying we're going to just take a function and we're going to try and figure out everything we possibly can about this function. And then we're going to collect all that information. This is almost like working a puzzle or solving a mystery. Once we figure out everything we can, then we're going to take all that information and see if we can figure out a way to try and sketch the graph or to have a clue about it. So now some of these things will not apply. Occasionally, sometimes things like intercepts are just too difficult to work out, so you skip them. So a lot of these things are not mandatory, but they can just help you. But of course, some things we do need to do. So the first one they ask about is the domain. Now this is like a polynomial. Domain for a polynomial. Domain is what are the possible values of x. The only time the domain is different than all real numbers is if you have any variables in the denominator of a fraction, or if you have any variables under a square root. We don't have a fraction. We don't have square roots. Therefore, the domain is all real numbers. Intercepts. Typically, y-intercepts are pretty easy because the way we find a y-intercept is you go into our equation, and once again, f of x and y are interchangeable, so I'm talking about y-intercepts. It may be clearer if I rewrote the equation or the function with a y. Y-intercept is where you set x equal to 0 and solve for y. So in our case, 0 cubed plus 3 times 0 squared minus 9 times 0 minus 13. Looks like the y-intercept is negative 13, or if you want to express it as a point, 0, negative 13, right? For the y-intercept, the x is always going to be 0. Now here's a case where if I try and do the x-intercept where I set y equal to 0, I have to try and solve this equation. If this was a trinomial or something, I could maybe try and do it. But this is like a cubic equation, and it's not a simple thing to solve this. There probably are some x-intercepts, but it's just not worth all the effort to figure those out. It's not really critical to know those, so I'll just say we're going to skip x-intercepts for now. Next thing is asymptotes. Asymptotes only apply really when your function is like a fraction or a rational expression. So for this one, they don't really apply, I believe. We'll see down the road if you have some asymptotes. What do they say next? Intervals of increase or decrease. So, all right. So intervals of increase or decrease, that's all about the first derivative. And this is what we've been doing for a while now. You take the first derivative, find the critical points, go in, divide up your graph into regions, and for each region, see if it's increasing or decreasing. So this should be something we're pretty familiar with. First derivative, 3x squared plus 6x minus 9. To find the critical points, I'll first set the first derivative equal to 0 and solve for x. I'm going to factor out a 3 as I write this. And actually, this 3 should disappear if I divide both sides by 3. This actually factors. This may have been the same thing we factored a few minutes ago. I think it's going to be x plus 3 times x minus 1. Looks like we have two critical points. And because there's no fraction here, there's no critical points from where x, or from where the function is undefined. So let's go ahead and figure out what's going on in all the regions between these points. So here's my two critical points. Three regions. I'm going to go in each region and see what the first derivative is, because that'll tell me whether it's a region where the graph of the function is increasing or decreasing. Positive first derivative, it's like a positive slope, it's increasing, and negative first derivative, negative slope means it's decreasing. Test point for region 1, how about -4 for region 2? How about 0 for region 3? How about 2? What I'm going to do is I'm going to, for each value of x, I'm going to calculate the sign of the first derivative. So let me write it over here just so it's clear, the math. I plug in -4 for x. This is negative. This is negative. Two negatives make a positive. Region 1 is a positive region, which means the function or graph is increasing. For region 2, if I plug in 0 for x, positive, negative. Looks like region 2 is negative, so the graph is going down. Region 3, if I plug in 2 for x, positive, positive. Region 3 is positive, we're back to increasing. So now I can figure out the intervals of increase or decrease. Increase is where the first derivative is positive. Looks like intervals 1 and 3. So -infinity to -3. And then 1 to infinity. Decrease is region 2. Now what's interesting from this chart, I can also determine if I have any relative maximums or minimums. Notice here, slope is increasing, gets to here, goes to 0, then decreasing. Looks like a maximum. At x equals -3. So if I go to now the transition from the second to third region, once again my slope is down, but then as soon as I come through, it starts increasing. So it looks like I have a relative minimum at x equals 1. The last thing I talk about is concave up and down and any inflection points. So all that stuff is determined by the second derivative. I'm going to go back, let me do it up here, because it's going to be pretty straightforward. Calculate the second derivative, 6x plus 6. Or if you factored it, x plus 1. So I'm going to set second derivative equal to 0. Solution is -1, which is the second derivative's critical point. I'm going to have two regions. Test point, -2 and 0. So what's the sign of the second derivative when x is -2? If I go up here, plug in -2, looks like the whole thing is negative. When it's 0, looks like it's positive. So it looks like going from, so let's say concave up, -1 to infinity, concave down, -infinity to -1. Then the inflection point is where the concavity changes signs at x equals -1. Now, based upon all this information, can I sort of kind of sketch the graph? Now, here's the place that a lot of times the information we've gotten, we want to get the actual points. In other words, here's the key. Here's the original equation. For instance, we've learned, first of all, important things for graphing. We know we have a y-intercept. (0,13), no asymptotes. How about, let's write down our maxes and mins. I'm looking at my other page, and we decided we have a max. Value of x is -3. Let's find what that actual point is. So if I plug a -3 into here, this is where you got to be careful with your math. -3 cubed is -27. -3 squared is 9, so that's 27. -3 here is back, since it's a negative, it's plus 27, then minus 13. Looks to me like it's maybe 14. I did this previously. I should check some of these to make sure I don't make a math error and make a mess out of this. Well, I may not have finished it, but I'm hoping I didn't make an error. We know that the minimum, the value of x was 1. So if I try and go get this point, I'm going to check this -3 again, just to be sure. -3 cubed, -3 times is 9, times -3 is -27. -3 squared is 9, 9 times 3 is 27. So those actually cancel out. And then -3 here is 27 with the negative, so it's positive 27. I think it looks correct. Now if I put a 1 in here, 1 cubed is 1, plus 1 squared is 1, 3, minus 9, minus 13. Looks like this is -22 plus 4. So now I can plot those points, and at this point Well, let's figure out my point of inflection. It occurred at -1, so I plug a -1 in here. This is -1 plus 3 plus 9. So -14 plus 12 looks like -2. So let's just plot these points and see if it even a little bit makes sense. Some of these values of y. So I've got to go like, maybe here I'll go -5, -10, -15, -20. And then maybe 1, 2, 3, 4, 5. It's 5, 10. So intercept was 0, -13. Maybe right here. I have a maximum at -3, 14. 5, 10. -3, 14. So I'll just draw a little, it's like a maximum, like something like that. Minimum at 1, -18. Something like that. Point of inflection, -1, -2. So here's where it changes. So as a guess, so increasing, looks to me like increasing, I think it's going to be negative infinity to -3, which is correct. So maybe I'll just and it looks like to me it's going to be decreasing from -3 all the way to 1, which is correct. And actually there's a point of inflection in here where it changes from, it goes through this point. It's pretty ugly, but when you're doing these sketches, it's hard to have it be nice and beautiful. Then my guess is that here it probably goes like this. So it's just confirm increasing regions, negative infinity to -3, and from 1 to infinity, decreasing with some -3 to 1, concave down with some negative infinity to -1, and then concave up from -1, and then the point of inflection, and the y. So that is a rough sketch, but that's the idea. All right, let's do one more. We'll go ahead and do 19. Maybe I'll start with a fresh sheet of paper, because these take up a lot of space. So here's 19. Same instructions as the last one, but the function is 3x to the 5th minus 20x cubed. Domain, it's another polynomial, so it's all real. Pretty straightforward. Let me factor this. I don't know if this is going to help or not, but I can factor out an x cubed. And I have 3x squared minus 20. Y-intercepts, if I set x equal to 0, so actually, looks like this graph is going to go through the origin. X-intercepts, because I factored, there's one pretty obvious x-intercept, well 0, which you already have here. There's another one here This is not going to be a pretty number, but just basically it's going to be I'm actually grabbing my calculator. 20 over 3 is like 6 point something. 6.7. So that may help us when we're graphing. So we're also going to have there's a couple of x-intercepts. Asymptotes, no asymptotes. Increase, decrease. All right, let's take first derivative. 15x to the fourth minus 60x squared. To find the critical points, I'm going to set that first derivative equal to 0. And actually, I'm going to save some time. I'm going to factor out a 15x squared. So I got x squared minus 4, which I can factor as a difference of squares. Looks like critical points for the first derivative. X equals 0, -2, and 2. So let's see what's going on in those regions. So we got 4 regions. If I do a test point in each region, region 1, how about -3? Region 2, how about -1? Region 3 is 1, region 4 is 3. I'm going to get the sign of the first derivative. Just to make it clear, here's the first derivative. So when I plug in a -3, you know what, this thing is always positive because it's x squared. So the key are these two parentheses. -3, this is negative, this is negative. Positive, when I plug in -1, positive, negative, region 2 is negative. Plug in 1, positive, negative. If I plug in 3, positive, positive. So I got positive, negative, negative, positive. Looks like I'm going to have a maximum here. Here it looks like a flat. And then here it looks like a minimum. So first of all, regions of increase and decrease. Where is the first derivative positive? From -infinity to -2, and from 2 to infinity. Where is it decreasing? It's where the first derivative is negative. -2 to 0 and 0 to 2. I would say I have a maximum at x equals -2 and a minimum at x equals 2. All right, now let's go learn some stuff about the second derivative. Let me just do it here. I'm going to base it off, here's my first derivative right here, so let's do this. 60x to the third minus 120x. Once again, it's probably going to help me to factor this, so I can factor out a 60x, x squared minus 2. Now for critical points, I'm going to set that equal to 0. 60 doesn't matter. Looks like x equals 0, and if you look at this inside here, it's going to be plus or minus square root of 2, which is like 1.4. So negative 1.4, which is negative square root of 2, 0, 1.4, 4 regions, test points, region 1, how about negative 2? Region 2, how about negative 1? Region 3 is 1. Region 4 will be 2. Going to get the sign of my second derivative, which is actually this right here. So I put a negative 2, I got a negative, and that's going to be 4 minus 2. I believe this whole thing is negative. I plug a negative 1, I got a negative here, and a negative here, which makes it positive. I put a 1 in, that's positive, and inside's negative. I put a 2 here, I think everything's positive. So you got negative, positive, negative, positive. So concave up, negative 1.4 to 0, and 1.4 to infinity. Concave down is negative infinity to negative 1.4 and 0 to 1.4. Looks like I have 2 points of inflection when x is, see, because z, actually 3 points of inflection. Negative 1.4, 0, and 1.4. Negative to positive, positive to negative, negative to positive. 3 points of inflection. All right. Let's see if we can figure out maybe what some kind of sketch of this graph might look like. So let's write down what we've figured out. Intercepts 0, 0, 6.70, negative 6.70. We have max, relative maximum, negative 2. Now let's plug in negative 2 into my, here's my function. 3x to the 5th minus 20x cubed. If I applied the negative 2 in there, negative 2 to the 5th, wow, it's going to be 2 times 4, 8, 16. Negative 32 times 3, I believe it's negative 96, minus negative 2 cubed is negative 8. That's positive 160. Looks like it's like 64. Wow. Minimum occurs when x is 2. So I put a 2 in here. I think I might get the same thing except opposite sign. Let's see. Put a 2 in here. 4, 8, 16, 32. 32 times 3. 96. 8. Negative 160. Yep, I think it's negative 64. Inflection points, they're sort of a pain. I can do one of them, the one where it's x is 0. It's 0. The other ones are negative 1.4, 1.4. We'll just try and graph those. So let's see what we got here now. This is never very, especially these huge numbers. So really, If I say 64, how about I go 20, 40, 60, negative 20, negative 40, negative 60. Intercept, first of all, here, 6.7, 4, 5, 6, maybe right here, and negative 3, negative 4, negative 5, negative 6, negative 7, maybe right there. Maximum, negative 264. Maximum? Oh, 64, sorry. Minimum 2, negative 64. So I think increasing is from this isn't going to look beautiful, but inflection points, let me see, I have an inflection point right here, but I also have an inflection point at negative 1.4. And 1.4. This is a case where, because of the scale of the graph, I almost hesitate to keep going because it's going to be confusing and messy. And actually on the test, the key thing I'm looking for, can you figure out all this information? The graphing oftentimes is just so messy that I think I'm going to stop here and say that, sometimes the graphing is, if I had some real graph paper or computer, maybe we could do it, but I'm not quite sure I can make sense of it, and it may be more confusing than anything. All right, so we'll stop now. We'll have, I think, one more video, and then we'll be finished up.